Okay guys, let's take a look at today's lesson. We are continuing to work with derivatives. Let's talk about what we've done so far. We've learned how to find all sorts of derivatives. We have learned to do different derivative techniques like logarithmic differentiation, implicit differentiation. We have learned some applications of derivatives like related rates. And we're going to continue on in this unit looking at applications of derivatives. How can we use derivatives? This lesson takes us to learning about increasing and decreasing, how the increase and decrease test, and the first derivative test. So we're learning a couple new tests today on using a derivative. Now, many of you have already had experience with this in pre-cal. We touched on this in pre-cal just a little bit on doing sign charts and finding intervals of increase, decrease, that kind of thing. So many of you are already familiar with it, so we're just going to go into greater detail and look at how you would use it. Okay, let's start with the increasing and decreasing test. It starts out like our theorems from yesterday, Rolle's and mean value theorem. We are supposing that f is continuous on the closed interval and it's differentiable on the open interval. Okay, that 1 and 2. That should be familiar to you. We looked, both of the theorems required that yesterday. All right, if that is true, then if the first derivative is greater than 0, in other words, if it's positive, then each point on that particular interval, at each point on the interval, then we consider it increasing. It's increasing on the closed interval. Okay. Likewise, if the first derivative is negative, less than 0, or negative at each point on a particular interval, then the function is considered to be decreasing on the closed interval. All right, so let's take a look at this diagram. It really gives us some examples of what that looks like. As we are moving along here, we can see that this is where the derivative is greater than 0. We're familiar with that. We've talked about that many times, right? The slope of the tangent line would be positive right along here. Notice that I have the first derivative being 0 here, and there is no max or min. Just because your critical number, you have a critical number where the first derivative is 0, does not guarantee that you will have a max or min. This is an indication that sometimes it will be something different. This isn't a max or a min, so just keep that in mind. As we continue to go, we can see that the functions continue to increase. The first derivative is positive, first derivative is 0. Now the function is decreasing. The first derivative is negative, and makes perfect sense because any tangent line that we would draw over here, the slope would be negative. All right, and here, let's look at this. This is where the derivative is undefined, which is a perfect indication of why we need two kinds of critical numbers. Not just where the derivative is 0, but also where the derivative is undefined, because it is possible, like in this case, if the derivative is undefined, to have a maximum there. It's a corner or cusp, so the derivative won't exist, but it still is a maximum value here. And here's another place where the first derivative is 0. So let's remind ourselves, when the first derivative is 0, it's called it's a critical number, but what is the special name for it? Stationary point. Okay? And when the first derivative is undefined, it actually also has a nice little name. It's the singular point. It's a great formula quiz question. A great formula quiz question, okay? What is the difference between a stationary point and a singular point? Right? Okay, so I throw out these great formula quiz questions and I don't see students writing them down. I throw them out there for a reason, to help you. The way my mind thinks. How do I come up with formula quiz questions? I'm trying to give them to you. As soon as we cover new definitions, new material, I try to throw out, how would I use that on a formula quiz? It's a singular point, and it's on the yellow sheet. It's on the yellow sheet. So we have, 4 pages of 2 pages, front and back of yellow sheet now. So just kind of throwing that out there. Okay, so that's increase-decrease test. Now let's look at first derivative test for local extrema. I will have to tell you it's my favorite extrema test. Okay, yes, I have a favorite test. That would be it. If I have a choice, that's the one that I'm going to use because it's pretty simple, it's straightforward, it involves a sign chart just like the increase-decrease. I use the same sign chart for both. Sometimes I'm not able to use the first derivative test, and then I have to fall back to the second derivative test, which we will learn in a day or so. But this one, first derivative test. So let's talk about it. Suppose that we have a critical point. C is a critical point of a continuous function, and it's differentiable at every point. Okay. This direction is important. Moving from left to right is how we have to read these graphs. Moving from left to right. If the first derivative changes from negative to positive at that critical number, then f has a local minimum. All right, so I'm going to draw just a made up sign chart down here, and I'm going to, let's talk about some, options. Let's just say we had something going on like that. Okay, so I did a sign chart on my first derivative. I found out the y values, if they were positive or negative on my first derivative, and so if the sign chart, if my derivative changes from negative to positive, so that would be like here. I'd be decreasing and then increasing. Some students like to draw that there just to basically indicate that's a minimum. If you want to, you can. That's just what some students like to do, so that they can just glance at the sign chart and know that there's a minimum value there. We're going from a decreasing function to an increasing function. We're going to have a minimum at that location. If the first derivative changes from positive to negative at the critical number, so like here, we're going from positive increasing function to a decreasing. And again, some students like to draw that, so just to indicate that that's a maximum. If we go from a positive to a negative value at C, then we have a local maximum there. If we have basically a place where the derivative does not change signs at the critical number, like here, we went from negative to negative. That means there is no local extremum there. That would be an instance like this. See, we went from positive to positive. That is a critical number, but there are no local extrema there. Okay? So that's what the first derivative test tells us. All right, and I need to make one more comment about our increase-decrease. We'll talk about it in relation to the sign chart. So we would be increasing from negative infinity to negative 3, 1 to 2, and 7 to infinity. Right? Now, I know you probably all think that mathematicians get along real nicely and they never argue about anything. That would not be true. So one thing they have big fights about is increase-decrease. There's one camp that believes that you should bracket those numbers in the interval, and there is another camp that believes that you should use parentheses. And I would tell you, it is very passionate on both sides. Okay, not for the infinity, but for the interval. So some would believe that here you would do this, and others believe you would do this. Okay? Now, the AP guys recognize that this is a point of dispute, and they take both. What I would ask that you do is just be consistent. Just pick whichever one you want to do and just be consistent. That has to do with increase-decrease. Okay? Yes, I know I have a little bit of a preference, but I'm not going to say what my preference is. We're just going to, either one is fine. Okay? Because that's out there. So either some books use this and some books use that. So either one is fine. All right, and I'm sure that those two camps of mathematicians have proofs to, have a beautiful, elaborate proof to show their own point. But we'll let them battle it out. Whatever, right? It's just parentheses or brackets, that's all. So we're just going to choose one and use it. Okay? All right, so with that, let's take a look and let's do our example. One other thing, sorry, I need to mention about the sign chart is many years ago, the AP guys allowed sign charts to be evidence on the test. Okay, a few years ago, they disallowed that. So we cannot use a sign chart as justification. Now that doesn't mean that I don't want you to do one. I think it's really good to do one, but I'm going to show you how we compensate for that. I'm going to show you what you will have to say as justification that's going to take place of your sign chart. Okay, so as we work through the problem, I'll show you exactly how you justify. So let's start. We just have one problem that we need to work. We want to find the intervals where f is increasing and decreasing. Okay, so we're going to do that. Identify all points. Probably on any given quiz or test, at least 10% of students will not read that. And they will just give me the x values and needlessly lose points. Please read. Please read. Because if it asks for points, it wants a point. Okay, both the x and the y value. So please pay attention to that. We want the points where we have a relative max and min, and we want to justify. Okay, we want to justify. So another issue we need to speak about since we're going into this, these topics are always on the test, period. I have never seen a test where these topics are not on it, are not used. You will be using these, and you will have to justify. Now, one thing that students get a little bit out of shape about is on the AP test, it doesn't always say justify. But many times, they give you points for justification. So they're like, well, how do I know? How do I know when to justify, when not to justify? My answer is always justify, because it's not going to necessarily say that. Now, if it does say that, you can bet that, you've got to. But I've seen free response problems where it did not indicate that you had to do justification, yet they assigned a point for it. No, multiple choice is just straight out, and you can even guess on multiple choice. They are not looking at work, they're just looking at the answer choice on multiple choice. But on free response, it is graded by a mathematician, and there are points assigned for every little thing, and you want to gain as many points as possible. So always justify, and I'll show you. It's very simple, very easy to justify. So let's work on that. So in order to do this, we need to find the first derivative. So let's do that. So f prime of x, I'm going to do the quotient rule, which we remember as fg minus fg, first things first, second things second, over g squared. Alright, so the derivative of the numerator is 2x. Copy paste the denominator. Minus, copy paste the numerator, and then the derivative of the denominator, all over the denominator squared. Okay, we are going to do a little bit of work with it, so I'm going to pretty it up. We need to find the critical numbers from it and all that, so I'm going to get it in a little bit better shape. So let's go ahead and distribute. And then just combine like terms. I'm going to go ahead and factor, because that just helps me with my sign analysis. I don't really like to do big numbers in my head. You probably have kind of caught on to that. So I would prefer it to be all factored out. Alright. So I need to find the zeros and the undefines. To find the zeros, I'm going to set the numerator equal to 0. For some reason, that really troubles students for me to ignore the denominator. I'm not ignoring the denominator because actually I really don't care what the denominator is as long as it's not 0, right? Because isn't, I don't know, 0 over in a million still 0, right? So I'm really just working with the numerator. I'm going to set it equal to 0 and find out what makes it 0. So we know that x is 0 and x is 1. So those are my what kind of critical numbers? Stationary points. Those are my stationary points. Okay, so now I need to find my undefines. So let's do that. So 2x minus 1 squared is 0, so I would square root both sides, solve for 0. Solve for x, and I get x is a half. And what kind of critical number is this? It's a singular point. Okay? So we have our two kinds of critical numbers. We're going to put them on a number line, and just for space, I'm going to go ahead and put them up here. We have, what do we have? We have 0, 1/2, and 1. Of course, I'm sure we recognize they need to be in, ascending order, right? I'm sure, hopefully, we recognize that. All right, so now I'm going to refer to my derivative. I'm going to do my sign chart. So if I put a negative number in here, now let's talk about the denominator. Does it really matter what sign of number I put in here? No, it's always going to be positive. So I don't mean to hurt the denominator's feelings. I'm just not going to be dealing with it, right? Because it's always positive. It doesn't matter what I put in there. So I'm just going to worry about the numerator. So I've put a negative number in the numerator. I get a negative times a negative, which gives me a positive. Let's see, we need a number between 0 and 1/2, so like 0.1. If I put 0.1 in here, I get a positive times a negative, so that's giving me a negative. All right, let's 0.7. 0.7 is between 1/2 and 1, right? So let's put 0.7. If I put 0.7 in here, I get a positive times a negative, which is another negative. And then if I put, like 5 in here, I'm going to get positive. So there's my sign chart. There's my sign chart on my derivative. All right, so now let's find our intervals of increase and decrease. Okay, so increase, we go from -infinity to 0. You can put a U there if you like, or just a comma. They really don't care. And then we go from 1 to infinity. Now here's where the justification comes in. You need to write this every time. On quizzes and tests, I'm going to be giving points for justification. You say, because, you can abbreviate because f prime of x is what? Greater than 0. We're increasing, right? Greater than 0. That's all all the justification you need. It is not a huge deal. It takes like 2 seconds. Please be sure. That is going to make the difference between you getting a point or not. So really important that you just get in the habit of writing it. Just write down the justification. All right, because again, they do not take sign charts as justification any longer. All right, so let's do our decrease. Decrease from 0 to 1/2 and 1/2 to 1, because if I'm using brackets, I would, but I'm using parentheses right now. Okay? Because f prime of x is less than 0. See? That's all. That's so important, and it is so simple. You don't have to write out, the derivative is negative, the derivative is, just do it in math symbols. Very easy. All right, so now let's see. We have that done. Check. Let's do our relative max and min points. Notice how it actually says justify your answers, but I hope I've made it clear that even if it doesn't say that, you still need to. Okay, like I said, they don't always say that, and yet they assign points. Why, I don't know, but that's just the fact. So we need to be sure to follow suit. So our maximum, let's look at our sign chart. So our maximum would be where we go from increase to decrease. So right here, so we have a maximum at x value of 0, but we want the point. So where do we go? Original. I go back to original. So I sub a 0 in here, and I get what? 0. Okay. Now here's the justification for a maximum, and we don't have another one. So because because f prime of x changes from, we're at a max, changes from positive to negative. That's it. F prime of x changes from positive to negative. That is as short as I can make that. Okay, minimum value. Actually, we want the minimum point. So we go back up here. Minimum is where we go from decrease to increase. So it looks like we have a minimum at 1. Now let's go find our y value. So 1 over 2 minus 1 is 1. Because f prime of x changes from negative to positive. Okay, that would be my answer with justification attached. It's just real quick. Okay, it's just remembering to do it. Please do remember. And then it says use your results to sketch the graph. Let's sketch the graph and let's see. Okay, and that, I know it's a weird thing, right? But it's relative, it's local, so it's not an absolute. Okay, so we know, let's write our points. We have a maximum at 0, 0. We have a minimum at 1, 1. Okay, so we have those graphed. Let's use our increase-decrease thing. So we go from increase, so over on this side of 0, we are increasing, which means we have to come from up down here, right? We're increasing. So we're going to come up like this. Now, what happens at 0? We decrease, so we're going to have to, come back down. And then at negative 1, there's something going on. What's going on at negative 1? Excuse me, negative 1/2. Positive. What is going on at 1/2? What's going on? It's an asymptote, right? At 1/2. It's an asymptote because, well, let's look at our original function. If we look at our original function, remember from pre-cal? If I set the denominator equal to 0, I get my vertical asymptotes. And so I have a vertical asymptote at 1/2. So let's go ahead and put that in, which means that this guy just goes like that. Okay? All right. So let's look what happens. What comes from the top? Well, see, between 1/2 and 1, I'm decreasing. Right. I'm decreasing. So to decrease, I have to, right, I'm going to have to come out this way. And then after 1, what do? I increase. So I go like that. So that's my graph. Kind of crazy looking, and it's a sketch. It's not perfect. If we wanted it to be perfect or more accurate, what could we do? Yeah, get points, right? Plug points, find points. But I'm not asking you to do that. We're just sketching. All right? So there is that. Yeah, there's asymptote at 1/2. Oh, yes, there is. There is. You're right. And that's excellent. How do we know that? And that is very true. How do we know there's a slant asymptote there? Yeah, it's 1 higher, right? 1 degree higher, so it's a slant asymptote. And if it was 2 degrees higher? I know, but it's so fun. It's a curvilinear asymptote. I know. It's like an asymptote, like a dotted line, like a parabola or a cubic or something. Isn't that so fun? That is so fun. Okay, curvilinear. Curvilinear. And there we go.